All right, section 13.1 we're going to get started with is called translations and rotations. And the first thing we're going to talk about is a little bit more general term than either one of those called transformations. So a transformation is simply a one-to-one correspondence from a plane to itself. All it does is it takes whatever the image is and it moves it somehow. Moves it up, down, left, right, turns it around, something. It just moves it. So it preserves all the properties that that image already had. You're not stretching it out of shape. You're not, like squishing it together. It's not Play-Doh, anything like that, okay? So it preserves all of the same image. So an example of that would be to take you in my class and you in the GC. You head to lunch after this, maybe or before. Okay? You did not change. You just changed where you were. Okay? Now, this is an example in 3 dimensions. It's the same in 2 dimensions, though. All we do is we pick something up and we move it. A one-to-one correspondence means that each feature in the first image is paired up with a corresponding feature in the second image. So let's say, for instance, you had a triangle. Okay? So you have this triangle. I need more space. Let me do it up here. Okay, here's my triangle. I tried to draw it so that the sides look like they're all different. Okay, scaling. And you take this triangle and you move it. That would be a transformation. And the one-to-one correspondence part that it's talking about is saying that every part of this image has a corresponding part over here. Every angle has a corresponding angle over here. Every vertice has a corresponding vertice over here. That's what one-to-one correspondence means.
So they have to be congruent.
They would. That's true. And we don't usually talk about it as being 2 separate images. We talk about it more like I talked about you here and you in the GC. It's more about taking one image and actually physically doing something to it to shift it somewhere else. That's the idea. So this is almost like we've just moved the triangle, not that we copied and pasted the triangle. All right, an isometry is any motion that preserves length or distance. Okay, so if you think about that, again, that would be the example of you or whatever else, that when you move it, you didn't change your height, right? You didn't change the length of your arm, anything like that. Those triangles that I just did, all I did was I took them from one place and I put them somewhere else. I preserved all of the lengths and the angle measures, all of the size, features that it already had. It was a preserving feature. And then we talk about it like what you just said, Elena, in the next part, right? It says we can say that 2 geometric figures are congruent if and only if they can be related by an isometry or a sequence of isometries. So if somehow we can take this image and we can sort of identify that the one-to-one correspondence did this, then the images created were congruent, just like you noticed. These 2 triangles are congruent because I have the ability to say this piece became this piece, and this dot became this dot, and this angle became this angle, and so forth. That's what makes an image congruent. Is every transformation also an isometry? Well, no. We can transform objects other ways too. Can you think of something that you have used before that you would transform it in a different way? What could you do with an object that would not be an isometry? It would not preserve distances.
You transfer a bag of oatmeal from the cupboard into the microwave, it gets bigger.
Okay, so something that enlarges it, right? Something that makes it change size and shape. So if you think about it, so that's a really good 3-dimensional example, Beth. If you think about a 2-dimensional example, you guys have used them before. You do them on your computer screen all the time when you hit the little button that changes it to be like 150% size, right? I don't know about you, but I do it all the time. Sometimes I want to shrink it so that I can see the whole page. Sometimes I want to blow it up so that I can see individual sentences or images on something. And copiers. Copiers are another place where you'll see that done quite frequently when you take an image and blow it up or shrink it down, okay? And I can do it on here too, right? So let me show you. You guys are going to get to have some fun with this another time. Many of you already have before. So here's my image, and I actually have the ability to make this larger. I have the ability to rotate it, and I can make it smaller. How cool is that, right? That right there is smaller than where I started with it. It's also got a rotation. I twisted it around some. The rotation's not a problem, but the fact that I did not preserve those lengths is making it not an isometry. Okay? So not all transformations actually are isometries. All right, so we're going to talk about some first, though, that are. So the first one we're going to talk about is a translation. Translation is one type of transformation that is an isometry. A translation moves every point of an object a specified distance and in a specified direction along a straight line. I wanted to say specified line. All you're doing is you're physically shifting something. So, like for instance, me, if I were doing me, two-dimensional me, pretend like I'm like Flat Stanley. You guys know Flat Stanley? I'm Flat Stanley right here. And all I would have to do to be a transformation is to physically move over here. I don't move my head, I don't shift anything. I'm still in the exact same position that I was, I'm just in a different location. And that's what a translation is. The original figure is called the pre-image, you know, the image before, the before image. And then the resulting shape is called the image. Okay, so the image is what happens afterwards, the pre-image is what happened before. We also sometimes will call a translation a slide, because it's an action that mimics the motion of a child sliding. So you've got a great picture here on the next slide of a slide. Yes? So the child, exactly the same position at the top as they are at the bottom, right? We're assuming they didn't like crack a smile or anything. They're exactly the same. All they've done is they've moved downward. Okay? Complete shift downward, no other changes. They've slid. Right? So if you want to think about a translation, you can think about the image of a slide. All you've done is slid it or shifted it somehow. All right, in a translation, the image of all points are determined by the slide arrow so that all parts move the same distance in the same direction. So obviously, if my hand moved 5 units to the right, my foot needs to move 5 units to the right as well, okay? I can't have my foot moving 5 units to the left or 4 units forward or something like that. That would not preserve these distance properties. So whatever happens to one part of the image has to happen to all parts of the image. No distances, angles, sizes, or shapes are changed by a translation. So I think that's supposed to say the image. So the image created by a translation is always congruent to the pre-image. And that was the picture and the notice that what Elena actually noticed when she saw my triangles, right? The image was exactly the same, congruent to the pre-image. Yes, Skylar? Well, we have only discussed one transformation so far. It's called a translation. So we're going to discuss some more transformations in a minute. Exactly. It's like a big category. Transformations is a big category, and translations is a portion of that category. Yeah. All right. So here is a geosquare is what they're called. So a dot grid is another name for it. And it shows how we can do this process. So it says determine the direction and distance of the slide arrow, and then move all points accordingly. All right, so a couple of issues here. It says, the example says, find the image of the polygon under the translation from x to x prime. And you're probably going to need to add some dots on the left and on the top in order to make this work, okay? So feel free to add whatever dots you need to do that, and I will do the same. So what this is telling us is that we're starting at x, and we're ending at x prime. And what we want to notice is how the dot x moved to the dot x prime. So what in the world did it do? It slid how? Like, describe it with left, right, up, down.
Slid it like a diagonal going upward.
Okay, but I need units and directions, like left, right, up, down, 1, 2, 3, 4s. Up 1, right 2. You guys with me? Kind of like slope, right? It went up 1, right 2. So what we're going to do with our image is we're going to take every point here and move it up 1 and right 2. So I'm going to start with just the top of this. What shape is this? Oh, don't tell me you already forgot. It's a pentagon. Good. It's a pentagon. So we're going to take our image and we're going to shift it up 2. So up 1 and right 2. So every dot is going to move. So this dot, for instance, if it moves up 1, that would be here. And then right 2 would be over to here. Okay? So this dot, in fact, I don't want black. Let me use purple. Moves here. This is my purple dot. I'll color coordinate. Okay. This dot right here, where will it go?
It'll go one more over from the purple one.
Yeah, I've got to have a couple more dots over here, so I'm going to add a couple more here on each of my spots. So it will go right here, yeah? And then how about this reddish one? Where will it go? Right over here next to the green, right? So all 3 dots went up 1, right 2. We have a few more to move. So evidently I need another color. How about yellow? This dot.
That's where the original red dot would be.
It is. It will end up being right here. Up 1, right 2, puts it on top of where the red dot was before. We will go to orange. Let's make our orange dot this other one over here. Where will this orange dot go?
Parallel to the new yellow and then underneath one of the red.
Okay, so I think this is where you're indicating. Does that look right to you? All right, great. And we have one more dot. Our last dot, we'll make it pink. Our lowest dot right here, pink. Where will it go?
It'll go next to the orange one.
Next to the original orange one, right? So right here. And then what do you think we're going to have to do to finish this image? Connect the dots, right? Like at the at Chili's or something like that, right? We're going to connect our dots. This isn't the best connect the dot picture right here, but it's pretty close. Okay? So you feel like you took the image, you picked the whole image up and you moved it up 1 and right 2. And we did it piece by piece to make sure that we got everything in the right location. Okay, does that make sense? Everybody good with that? That's called a slide or a translation. All right, so we're going to do another one where it represents it in terms of the Cartesian coordinate plane. So we used the phrase up 1, right 2. Yeah? And now we're going to do that with x's and y's. So we can also explain the translation using coordinates from the Cartesian plane. The translation shown from O to O prime is applied to triangle ABC. So let's take a look down here. O, whoops, let me get my black. O to O prime. So let's just use the words we described a minute ago. How would we move that move?
Over 5 down 2.
Okay, and by over you mean right, yes? So we would move right 5. Okay, so think about it. On the xy plane, when you move things left or right, does that affect your x value or your y value? Your x value. So you're changing the x value and you're increasing it, because you're moving it right, by 5. So this value here that says xy, and it's got this arrow, goes to x plus 5. We simply add 5 to the x value. All right, and then we said we moved it down 2. Well, if moving things left and right corresponds to x, then moving things up and down corresponds to y. And if we moved it down 2, what would that be doing to all of our y coordinates? Subtracting 2. Yeah, so we would have y minus 2. So we add 5 to the x values, we subtract 2 from the y values. And in general, we can describe this as follows. We take the x value and we add a to it. We take the y value and we add b to it. A or b could be negative though, right? Just like our minus 2, y minus 2 was a negative 2 at the end. So that's totally, totally fine. All right, so I think we're going to do an example of one of those now. Yes, yes. It says to draw the image of a triangle ABC under the translation xy goes to x minus 3, y plus 1. So I'm going to let you guys give it a try, and then we'll check back in. All right, so somebody in words tell me what this transformation, this translation is telling us in words.
It's going to be 3 to the left of the original and 1 up of the original.
Okay, so Amy says 3 to the left and up 1. Does that sound okay to everybody? Excellent. Let's do that with the points A, B, and C. And as we go, we'll actually label them because that's how you're going to be best able to tell me where you ended up anyway. So if I take point A and I move it left 3 and up 1, so here's 1, 2, 3 to the left, and up 1, I end here, right? What ordered pair is that?
-4, 2.
-4, 2. You can also call it A prime. You'll see prime noted as the image points, just so you're aware of that. Let's do point B next. If point B is moved, what are you going to use?
-2, 5.
Does everybody get -2, 5 here? Yeah? Okay. So this is the point B prime. Nice. And our last point is the point C. So where will C end up?
0, 0.
Yeah, it'll end up at 0, 0, the origin, right? And that's C prime. And then what do we need to do? Connect the dots. And again, if we did it right, at least visually we should be able to look at it and sort of check, confirm, did we get a congruent triangle to what we had before? And we did. Okay, so I think this next one will help with Skylar's question earlier about the difference between transformations and translations, because this is our second transformation. Okay? So this one's called a rotation or a turn. It's another transformation that's also an isometry. It preserves distance, all right? Because I'm not going to do it, but if I stood on my head in the classroom, right, if I stand right here, like this, you know, and then I do it on top of this, and it would be bad because I'm dressed in a skirt, right? This would be awful. Okay, but I wouldn't have changed my height, right? Wouldn't have changed my arm lengths, wouldn't have changed the size of my face. None of that would, my face might get red. That might change. But I wouldn't have changed the sizes of anything. That's what a rotation is. It doesn't have to actually be spinning it, so to speak, but it could be. It could just be turning it 180 degrees, you know, upside down, quote unquote. So rotation is a motion of a plane determined by holding one point, the turn center, fixed, and rotating the plane in a certain direction. And we have to identify which direction, clockwise or counterclockwise, because it will make a difference. Okay? So the first thing we're going to talk about is one way to do it with tracing paper. So physically, one option if you're trying to rotate something is to use tracing paper or just another sheet of, you know, light enough thickness paper that you can see through it. Doesn't have to actually be tracing paper. So what's the idea? Well, here's your picture of your pre-image. Okay, so it's the ABC here. And this one, the blue dot, is what they're calling the turn center. So you hold this center fixed and you rotate the tracing, you rotate the tracing paper around. So you trace on top of the tracing paper, the brown paper on top. It's the white paper underneath is what has the actual image on there. Trace it on top, and then you take this and you rotate it but hold this one point O in the middle fixed. So you see the hand that's holding the point O here fixed, and it's rotated the piece of paper. Here's the image underneath that we were tracing, right? And this is the image that got rotated. So this would be an example of rotating it. It looks like it's being rotated. Well, it's clockwise, right? And it looks like it's a 90-degree rotation, or at least close, right? Maybe not exactly 90 degrees. But it's definitely a clockwise rotation. And you can definitely see from this image, too, that if we rotate it counterclockwise, we would be in a different location when we're done, right? We'd be over here somewhere instead. Okay? So this is one way to do it, is with tracing paper. In a rotation, the images of all points move along a circle by the same amount and direction, which is called the turn angle. So like you guys identified, it looked like it might be something like 90 degrees. That would be the turn angle. Okay? The direction would be clockwise or counterclockwise. The entire original image is picked up and turned all at the same time. So no distances, angles, sizes, or shapes in the original image are changed by a rotation. That's what makes it an isometry, right? We don't change any of those distances from before. What happens if you turn something 360 degrees? It's the same thing it was before. That's what this last point says. A 360-degree rotation around any turn center turns the point or figure back onto itself. That's called an identity transformation. Identity transformation. All right, a couple more slides. A 180-degree rotation is called a half turn. So you see my picture of somebody standing on their head, right? You just thought I was laughing and being funny before. There's the picture of the, but it's not. I'm not actually doing it in class. I'm just showing you a picture. Standing on your head, that would be a 180-degree rotation. You can see the turn center is halfway in between, say, the right foot of the character, right? The second image is an image more like a flagpole or something like this. And then the third image looks like the semicircle. Now the turn center doesn't necessarily have to be a point of the object that's a distance away. It certainly could be. All of these images are, right? The dot is not anywhere on the physical object that it was on to begin with. But it could be. The image could be done that way. Well, I'll draw it on here. I was about to draw on the board. I don't know why I was going to do that. So let's say you had an image. Okay, so you had this image and you wanted to turn it, but the point you wanted to turn it about was this point right here, the actual point on the image itself. That's totally fine. Let me see if I can do it though. That is with the technology, not can I actually do it. I can. I didn't need to do that. I'm going to try and do this without messing up the lengths of it. I don't know if I'm going to be successful. Okay, I'm not perfectly successful, but I think I'm pretty close. So if you actually have a point on the image itself when you're turning it, then that point will never turn, right? It didn't change because it's on the actual location that you're holding still, holding fixed. So this image right here would be a turn center that's actually on the object. Now we will use some nice rotations such as 90 degrees, 180 degrees, 270 degrees, 360 degrees. Those are the nice rotations. And a dot grid works really well for visualizing rotations as long as you have nice angles to rotate around. So we're going to do an example with a dot grid with a nice image. So we're going to find the image of the following quadrilateral. What kind of quadrilateral is this? It's trapezoid. Very good. I think you guys did learn something from chapter 11. I'm so glad. Trapezoid. And we're going to turn it 90 degrees counterclockwise from point O. And you can see point O on this one actually is on itself, right? Yes, ma'am. It doesn't have to be. They're just using that sort of as a default. Yeah. No, they're just using it that way. It doesn't have to be called O. It can be called anything. It's kind of like, you know, when we graph things in the coordinate plane, we typically use X and Y. There's nothing special about X and Y. Like the example that we did with the muffins and cookies, we used and C. That was fine. Yeah. All right, so we need to move these 90 degrees. So we want to think about taking this image and rotating, what did it say? Counterclockwise. So counterclockwise means this way, right? So if you take this image and you rotate it, you're going to rotate it up. Agreed? Okay, give it a try. See if you can move this image. Remember, you're totally preserving all the lengths. Keep those all the same. And rotate it 90 degrees counterclockwise around point O. Around point O, the turn center. If you're not sure, it's okay. We're going to do it together. But just give it a shot. See if you can figure out what it should look like or what you think it should look like. Okay, so with rotations, instead of moving individual points, it's often easier to move the line segments or the side images. They don't necessarily have to be segments, they are segments here. So let's think about it as moving segments instead of actually moving lines. So let's start with this segment that's on top. If I take this segment and I move it 90 degrees counterclockwise, it should turn to here. Did you guys get that? Okay, so I'll use orange. So this image becomes this right here, right? So here's my image right now, just this part. All right, how about this piece down here? Where will this move if I rotate it counterclockwise?
It's going to be on the bottom at O to that point.
Right, it'll move on to the other line segment I already had. So now we have this piece right here. How about this length of 2 right here? Where will it rotate?
It'll go up on top of the line you just drew.
Yeah, so it has to rotate all the way around to being up here. So this piece right here, if I continued it, would be up right here. And you almost get the last one for free, right? I mean, they have to connect the 2 endpoints together, and that's actually the reason I saved that one for the last, because it's the most difficult to rotate, I think, because it is at a diagonal. So if I rotate this one 90 degrees, it's going to end up here. Okay, so we checked to make sure it really preserved everything it was supposed to preserve. Do I have all the same lengths that I had before? Yes, I do. And that's what I was supposed to preserve. All the same lengths, the same sizes of angles, and so forth. So we're all good with that, yeah? All right.